So the best way to approach this problem is, I think, to, if I can get my pen going, to look at each of these as individual normal distributions. So I know that this is going to be 140. So I'm looking at the first one right now. The mean is 140. Standard deviation is 20. So that's going to be 120 right here. And the next one down is 100. So I'm only looking at this range right here. All right, so if I kind of visualize that one like so. Okay, now if I try the next one, let me erase some of the stuff that's going on. All right, well, I erased too much, but whatever. All right, so now for the next one, it's going to be 10 is the mean, and the standard deviation is 1, so that's going to make 9 and 11. I'm going from 11 to 12. Well, hey, that's actually the same area for this one, but now it's going to be on the upper side. So these two are pretty equivalent. I bet I can do better than this, but let's see what the next one shows. I'm actually going to jump down to D because that's what everyone thought the answer was. So in this case, I've got 1,000 for the mean, and then 1,120 is the first standard deviation away based on this. So I'm looking at this area. Okay, that's obviously more, so I can rule these two out. D is definitely the best one so far. Let's see what C is going to have us do. All right, so I will erase this, and now I've got the mean for this one is going to be set at 0. The standard deviation is 1. Sorry, that's -1 and +1 now. And here's -2. Now this is going from -1.5 to 0. So this is going from here all the way up to 0. So actually the answer is the one that no one picked. So 0, this is actually represents the biggest proportion of its distribution. So this would be, I mean, just guessing right here, that's going to be about 40%. I'm kind of making up some numbers here, but it's about 40%. All right, and this one only represents about 34%. So it's close. Most people thought D, but it is actually C. All right, and I think the whole point of this just goes to show the biggest numbers don't mean anything necessarily. We're talking about the highest proportion of the data for its respective distribution. Okay, so hopefully that answers any questions, clears up any confusion. Now, hopefully you guys read chapter 7 just to give yourself kind of a heads up. Some of the stuff I pulled straight from the chapter. But anyways, before we, the very first thing, we made progress, guys. This is joyous news. Okay, so we started at least varying. We're going to see this after every test, and you might not care, but you're going to care at the end. All right, so we got we've made it down to Redwall Cavern. We made it past Vasey's Paradise. I'm actually going to skip over some of this today, but look at this. We've got Redwall Cavern right here. It's one of the most famous scenes in the Grand Canyon, and we'll just quickly show you. This is it's a YouTube. Oh, I don't want that. Never mind. Sorry. We're just going to go back to the presentation. I thought it was something different. All right. So we're good to go with this. Random notes. So going over tests, and this is very random, but when we take a test, I don't take class time to go over it and say what you should have answered. Part of that is because sometimes people don't take it all at the same time, and so I can't just do that in class and kick people out. But also, I mean, I just don't have really time for that unless. So here's the basic idea. I want you guys to be aware of it now. If you ever want to go over your test, you certainly can, but you'll just need to hang out after class. And especially if you've looked over your test and you're not sure why you missed certain problems, we can go over it and I'll explain what the answer should have been and why. So if you're looking for me to take during class time and go over the test for everyone, that's not going to happen pretty much ever. But it's always an option for you to do if you need help with something. Now, another thing, of course, finding out what you did wrong after you took a test is somewhat helpful, but it's better to know what you're doing wrong before you take the test. So if you go over the AP progress checks and you want to go through problems like that, and if you've been doing that, you might see that your tests have questions that look pretty similar, to, at least in style. So if you do the progress checks and you want to go over those before the test, of course, certainly we can do that too. So just a random note I wanted to throw out here earlier in the semester, because I didn't explicitly say anything like this before, but I want to make sure it's clear to everyone. The other thing, I guess, related to progress checks is I opened up, if you go to AP Classroom again today, and I opened up the AP Unit 2 progress check. So you can start taking that now. And you might or might not want to start it today, but you can look through it. And that is, like I said, the progress checks are one of the best things you can do is review to help you for the test. So if you have more questions on this, let me know, but the progress check is available. Progress checks do need to be done for credit, but I grade it only for correctness, or only for completeness, not correctness. So keep that in mind. Okay. Again, if you have more questions on that, if there's something that I didn't cover clearly, please let me know.
When should we enter that we did that in that little module on Canvas?
Anytime you want. It's a good idea to do it at the time you finish it. But the deadline is, and actually I'm glad you asked that question. The deadline is the end of the semester. So if you want to wait, and I already said this, but if you want to wait to the very end and just do all your progress checks at the end before I submit grades and I get those grades in, that's fine, but it's probably not the best idea. But I will at a certain point start putting zeros in. That really, I put the zeros in because some people, if you don't have the zeros, you forget that it's something you need to do. So if you don't get them done, I'm going to start putting zeros in probably in a few weeks. I don't know exactly what date to tell you. So I will probably start putting zeros in just as reminders like, oh, shoot, I forgot to do that Unit 1 progress check. So I need to go back and do it. Something like that. Okay, but when you do it, you get full credit. You don't get half credit or anything like that. I'll just put the zero there, you do it, you submit that you've done it, and then I give you the full credit. Okay, I've said enough about that, unless you guys have any questions about anything so far. Okay. So let's talk about chapter 7, and here we go, scatter plots. This is not completely new stuff for you, though some of it you will have had to relearn. So one of the key ideas is that with scatter plots, we're comparing two quantitative variables, just like our two-way tables were for two categorical variables. So categorical variable 1 and categorical variable 2. That's what a two-way table is for. A scatter plot is for two quantitative variables. So here's quantitative variable 1 and quantitative variable 2. And of course, we end up with something like this. Okay, very good. So that's the basics of a scatter plot. And each scatter plot point represents a unique case and the two values that are associated with it. So for this point right here, the x component of it and the y component represent those two variable values. So in this particular case, we've got somewhere around a 100 for the IQ and somewhere just above 60,000 for the per capita income. And those are both related to the same country in this case. So we're going to be looking at this data set a few times during the course of today, but we'll be seeing some other scatter plots. So the x-axis, it shows what's called the explanatory variable, and the y-axis always shows the response variable. And the explanatory one is just like the name implies, it's the one that we presume has some kind of causal effect. It explains the response variable. All right, so if we compared vehicle weight to tire tread life, we would presume that vehicle weights would affect tread life, but it wouldn't make sense to presume that tread life has any bearing on vehicle weight. So if you're following that causal link, the heavier your car is, the lower your tread life will be. All right, we see that in this diagram, national IQ, and that's what this is referring to, like the IQ on average of people in the country, is explaining the per capita income. And of course, we might find that to be a controversial hypothesis, but regardless, the graph is suggesting that. Okay. And actually, there's a question here. It's kind of being covered real quick, but go away. Could the cause and effect be flipped here? Maybe just think about that right now, because we're going to come back to this graph and we're going to talk about some of the, well, we'll just kind of talk about this idea more. Okay. But you can think right now, could those cause and effect be flipped? All right, correlation. This is a big one. Again, you've probably worked with correlation before in one of your previous classes. But a correlation is basically, it's a correlation coefficient, and it's a way of quantifying the strength of the linear relationship. So there you go. The correlation coefficient is always R. So that is going to be a letter reserved for that particular quantity in stats. And here's a couple of formulas for it. These are actually saying the same thing. And what you can see is this sum of this is the z-score of your x values and the z-score for your y values, the sum of all of them multiplied. So if you take a particular value, you have your x and your y. This is your z-score calculation. I don't want to go too much into depth on this because we will never ever calculate this by hand. But it is worth understanding that we're basically multiplying some z-scores together for every single point, and then adding up all those multiplied z-scores, and then dividing it by n minus 1. Okay, the value of your correlation coefficient can range from -1 to +1. And either extreme represents a perfect correlation. So that would be literally like an algebraic relationship. So you have a straight line, and all these points fall directly on that line. That would be a perfect +1. This would be a perfect -1 right here. This is highly unusual with real world data. A value of 0 would represent no relation at all between the two variables. So hopefully as you're hearing this, you're saying, yeah, this all clicks. I remember hearing about this in the past. Or if you haven't heard about it, make sure you're double checking everything you're reading today and backing that up with your reading as well. Correlation conditions. These are important. We need to have quantitative variables. We cannot do correlation between categorical variables. So both variables must be quantitative. So if you want, this is to determine if you can even correlate two things. So first of all, determine, are they quantitative? Yes, they are. That's good. So if we want to do correlations, we also need to make sure that the relationship between these two variables is linear. And just to make sure it's very obvious, linear, it just needs to be in some kind of linear pattern. So that, I didn't draw that very well, but this is linear, okay? But if we had a scatter plot that did something like this, then we can see this has a curve in it. It's not linear, so we can't do any correlation on that. The correlation doesn't work. And we will talk much later. It's actually not something we're going to worry about right now. We can talk about transforming nonlinear relationships into linear ones, but that is not something we're going to worry about. And I will talk about it briefly during today. And outliers. If you see outliers, you have kind of something you can do. You can report the correlation both with and without the outliers. We're actually going to spend a day talking about outliers and other types of points, but here we go. Let's say we've got this lovely scatter plot. It's a very nice correlation going, and then you have this point right here. So what you can do is, if this is real world, what you'd want to do is you'd want to investigate that data point. Why is that data point there? Was that something really weird that happened? Was it misreported? Was it just input incorrectly? Because that can happen. So you would do some real world investigation. For AP stats purposes, what you could do is you could say, well, the correlation is, R is 0.92, but when I add this outlier in, then the correlation becomes 0.89, something like that. So if you report with and without, that's something you can do. Okay, now just a brief comment. I did grade the Unit 1 test where most people missed points, and I'm not talking about the multiple choice part of it. I'm talking about the FRQs where people were missing points. You guys generally had the right idea of how to answer, but remember we talked about using DISCO to describe distributions. So I'm going back to Unit 1 real quick. And when I was grading the test, a lot of people were just putting like a couple of things to describe the distribution. They'd say, oh, it's bimodal. It's like, it is bimodal. I'll give you that. What about the spread of the data? What about the center? What about, are there any outliers? And so if you didn't give that full rundown of what the distribution looked like, then you missed points from that. Though I didn't grade it overly harshly, I do want you guys to be aware, make sure you run through and describe everything that's expected. So DUFS is going to be our way of describing scatter plot relations. Okay, and this is just an acronym, and so here we go. D for direction, unusual features, form, and strength. All right. And again, remember, you can have notes available while you take these tests. So if you, and there's some of the references that I put up on Canvas have this information on it. So if you just want to have those available and you can think, if I have a scatter plot and I need to describe it, I need to use these 4 things. So we'll run through what these are, but make sure you hit all 4 of those. Direction, pretty straightforward. I would say everything with scatter plots are fairly straightforward. All right, the only information that matters is whether it is positive or negative. Of course, it could also be no relation at all. This would be one where your correlation coefficient is basically right at 0. So there's no direction in that point. It's a positive, negative. Well, there's no relation between the two. But positive, of course, we're talking about, is it a positive slope or a negative slope? And it says right here with the second bullet point, if you know the correlation coefficient, you can refer to that. So this might be a negative 0.9. This might be a positive 0.8. So you could say, oh, well, the correlation is positive, therefore it is a positive direction. But it's, if you have the scatter plot, it's easy to see it either way. Okay, unusual features. So remember, just say positive or negative. If there's no relation, you don't need to worry about that part of it. Unusual features. So this is going to be chapter 9 where we go into more detail with it. But an outlier, if we just want to focus on that for right now, it's any point that falls far outside the overall trend of the data. So we don't have, when we talked about outliers for box plots, we said we had our rule, right? That was 1.5 times dot, dot, dot. But when we talk about outliers here, we just want to point out anything that looks unusual. So go ahead and you can write on the screen, circle anything on this that you might consider to be an outlier. Okay. Hopefully everyone, now, if we had more data points, maybe we find out that that's not an outlier and that's actually the trend of the data. But based on the data that we have right now, this one is definitely an outlier. And then, yes, some of these, you might have your eye on some of these right here. These could potentially be outliers that maybe they fall close enough to the data that we don't consider them like that. So, but the one obvious one that right now I would call an outlier. Okay, so there we go. Not earth-shattering concepts right now. All right, form. And this is, okay, well, let's just jump into it. Form refers to whether the scatter plot appears to show a linear trend or a nonlinear one. So basically, form, is it linear or nonlinear? And so for right now, we're not going to worry about, and actually in general, we're not going to worry about if it's, oh, this is an exponential trend. This is a logarithmic trend. This is a quadratic trend to the data. We don't care about what it is right now. We just want to decide, is it linear or nonlinear? Okay, so if we look at these two, we could probably quickly see this one. I could draw a best fit line right here, and it looks linear. This one right here, I would probably want to draw something that looks like this. That seems to be a best fit line. And so I think between the two, we can see this one's definitely linear, and this one is nonlinear. So what we'd want to do is we'd want to comment about that. If I ask you to describe this scatter plot right here, then you would say it's a positive, nonlinear uh, relationship with an outlier. Now we haven't talked about the last bit of it, the strength, but honestly, if it's nonlinear, that kind of negates the last part of it. Okay, so the form of it, linear or nonlinear, and finally the strength. Here we go. Strength refers specifically to the clustering of the data around a linear trend. So the stronger the association, the higher the correlation. And of course, higher correlation can mean closer to positive or -1. And while a correlation coefficient will range between -1 and 1, frequently what we want to do when we're describing it is we won't give the actual correlation number. What we'll say is it is a strong, positive, linear relationship. So when I say positive, strong, linear relationship, that's already giving the direction, the form, and the strength of it. That one phrase, positive, a positive, strong, linear relationship between the two. Okay, so we can look right here and we can see what different kinds of correlations look like. And it's hard to read these numbers, but this is an R of, I believe that's -0.3. So even though it looks like not much is going on, there is a little bit of a negative trend right here. And I want to point out right now that -3 or -0.3 has nothing to do with the slope of the line. So this could be a -0.3 that has, a slope like this. It could be like this. So the slope of it we will determine differently. But for right now, the important thing is that it's negative, but there's not much of a relationship there. So it's not very strong. We call this incredibly weak, almost no relationship at all. This one is a positive 0.5. So this one's much more visible, and you can see it's positive. Anyways, negative, positive, negative. But of course, we're not worried about the direction as much here. We're seeing that as these numbers get closer to 1, so this is a -0.7 right here. This is a 0.9, 0.9. I think that's what it says. And this is -0.99. So you can see how the clustering of data around that linear trend gets tighter and tighter the higher the correlation. Okay. So again, use these kinds of words when you're describing it. Okay, and I also want to add, sometimes you might read in books where it says, oh, perfect means 1.0. I'll use absolute values here. Strong means, oh, from 0.99 to 0.7. We don't use specific ranges to determine if it's strong, perfect, or anything else. We just look at it, and if it's, because strong and moderate and weak are very subjective, but as long as you can justify it, you can pick whichever one. So hopefully I'm not saying too much here and confusing you more than helping, but let me know if you have any questions on any of this. If you think Duff's, it is pretty straightforward. Okay, so what I'm gonna do is I'm gonna give you guys a few different scatter plots to look at, and I want you to think about it for maybe 15 seconds, and then if someone wants to share what they think, how they would describe the scatter plot using Duff's. All right, so here's your first one. All right, now that I've got this written down, Make sure you hit all 4 of those. Anyone have any thoughts about how you would describe this?
So would you say that for the direction, you'd say in a negative direction, it has an unusual outlier. It's approximately 75, 475. The form is linear with a moderate strength.
That seems pretty fair to me. Yeah, I could agree with that. And we could, maybe someone else doesn't think that's an outlier. Maybe someone else agrees with you it's an outlier. It's one of those things that if you aren't sure if it's an outlier or not, you can always just hedge it by saying a potential outlier. And we're gonna, like I said, in chapter 9, we're gonna dig more deeply into an outlier and stuff like that. So, but I think that was a good description of it. Okay, next one.
I think I'd say it's in the positive direction with no outliers, and then linear with a strong strength correlation.
Okay, strong correlation. Very good. I agree. I hope everyone else agrees with that. And I'll just say in general, don't take this as any kind of a correction of anything what anyone just said, but you don't have to go in this order. You just need to hit all 4 of these. So like a really quick description of this one is you could say, this is a strong, positive, linear relationship with no outliers. Okay. And, but as long as you hit everything, it doesn't matter if you say it that way or you say it in different wording. Okay. Next one right here.
I would say maybe no relation, and then because of that, you can't really tell if there's outliers or not. Yeah, can't really tell if it's linear or nonlinear, and then probably, yeah, weak or no association.
There you go. That's pretty good. And just to that point, because you were talking about it with everything you were just saying, if there is a real form that's visible, you can talk about all 4 of these things. But as soon as there's like basically no relation, then, well, direction doesn't matter. We don't have any outliers if there's no form. So all we really can talk about is the strength and say there's no association. So some of these are kind of optional in certain scenarios, if that makes sense. Even here where we didn't have an outlier, we did talk about, in the sense we said, there are no unusual features, no outliers or anything like that. All right. So last one right here.
For this one, the direction is positive, no unusual outliers. The form is linear, and there's like a moderate strength.
Okay. I think that could be justified. Does anyone see it differently?
So I would have said that there's a positive direction, an outlier at 1905 and 40. The form seems to be nonlinear, and the strength is like moderate to weak.
Okay. And All right. So I'll just assume that that kind of covers maybe what the different opinions on this. No one thinks it's a negative trend. And maybe you do or don't agree that's an outlier. But I think the big thing with this one is it linear or nonlinear? Because I could throw that in there and a lot of you could say, yeah, that looks like the trend line. And then maybe I could just throw this in right here. Well, that didn't look very good. But I could throw in something like that. And maybe you decide that that one looks pretty good. So it's, if I was going to describe it, I would probably agree it's nonlinear. And the thing with our strength, this is another one of those exceptions. So I'll just put the acronym back up. When it's nonlinear, then that means the strength that we talk about is the strength of a linear relationship between it. So we could really just say it's nonlinear. We can still talk about the fact that there's a potential outlier and that is positive. But really the strength only matters if it's linear. So in general, I'll go ahead and tell you, if you're going to describe something using Duff's, it's almost always going to be linear. But just keep in mind, if it's nonlinear, you can kind of say that right off the bat. This is nonlinear, so everything that we do doesn't matter. And if it wasn't clear already, we are only going to deal with linear scatter plots when we're doing our calculations and other things related to it. So if it's nonlinear, we don't have a method for that right now. And we're just going to say, well, it's nonlinear, so we can't do anything, essentially. Okay. So here's what I want you guys to do real quick. And there's only, a dozen of us. So I'll probably just split you into 3 groups. So group 4, we won't worry about. We'll just kind of answer that one. So I'm going to put you into 3 groups and you'll find out which groups you're going to be in a second. And I want you to look at these scenarios and suppose that you're going to make a scatter plot. Which one would you call the explanatory variable? Which one would you call the response variable? All right, so there's one question. What would you expect to see? And what do you think the direction, the form, and the strength of it would be? Don't worry about outliers. We have no idea if there would be outliers. But the other 3, what would the direction, form, and strength be? All right, so you can look at that for a second. I'm going to get the breakout groups ready. Okay, and once you feel like you've, all right, so now you can see which group you're going to be in. And so look at your specific scenario that you're going to be looking at. Talk about it for about 2 minutes perhaps, and then we'll come back. Let's go ahead and get started. And so anyone from group 1, if you talked about those 2 variables, which one is the explanatory variable? Which one's response? What do you think the scatter plot would look like? Go ahead.
I think group 1 was a bit confused
Okay.
because I was in group 1 and I was confused. So that's why I'm saying that.
Okay, well, let's look at it now and maybe we can kind of talk through it. So you're looking at long distance calls, the time and the cost of the call, which is kind of a weird thing. This probably made a heck of a lot more sense whenever people were dialing off of landlines and making long distance calls. But anyways, what do you think explains? Does the cost explain the time that you spent, or does the time you spent on the long distance call explain the cost?
The latter.
Okay, so, and this is actually something I want to suggest you guys do every single time, any problem, because you can do a quick drawing real quick of all this stuff. And this is a good way to just visually draw out what is happening. So we think that time would explain the cost. All right, and I think that's right. So time is the explanatory variable, cost is a response variable. Okay, now what do you think would happen? As time increases, what do you think happens to the cost? Does it go up or go down? Anyone can answer.
It'll be positive.
Positive. So we would probably expect some kind of a positive relationship going on. I'm just randomly drawing a scatter plot here. So as our time goes up, the more time you spend talking, the more money you're going to be charged for the call. So we would expect a positive trend. So for Duff's, we could say it's going to be positive. Okay, now, but again, we're not going to worry about unusual features, but would we expect this to be linear or non-linear?
Linear, right? Because time is a direct correlation to money.
Well, and yeah, typically, and this might be kind of a lost metaphor or a lost concept. I mean, I think you get the idea, but of course, you've probably heard of like, oh, it costs 10 cents per minute to call international, or it costs X number of cents per minute. So it's a very linear relationship. All right, so we'll say linear for this. And the strength of this, what do you think? Is it kind of a moderate strength, strong?
I'd say moderate,
Okay,
but that's just off of pure intuition. And I
Okay.
can't really back that up with anything.
all right. Anyone else have some thoughts?
I would just say strong because there's already probably a preset cost for the amount of time.
There you go. So if we know we're going to be charged a certain amount per minute, not only is that strong, that's actually a perfect relationship because it's algebraically defined. But let's say that we're looking at all long distance calls, it's probably still going to be pretty strong correlation. So it might be something like this. But if we're only dealing with like one company, and I hope you're following along with what I'm saying here, this might be a lot of different companies combined, and they have different rates. So in general, it's going to be a pretty strong correlation between the time you spend and the money. But if we're dealing with one company, it might be a perfectly defined correlation that says, oh, you spent another minute, it's going to cost you this much more. You spent another minute, this much more. So it could be perfectly algebraically defined. So bottom line, strong or even perfect is possible for this one. Okay, group 2. Hopefully there's less confusion on this now. Group 2, what did you guys think?
We said that we would put the distance as the explanatory variable, and then
Okay,
the time delay as the response variable.
all right. I think that works for me too. Now, what about the time? Okay, the distance and the time delay. Sorry, I'm not making that clear. The direction of this. As the distance increases, what happens to the time delay?
Positively increases.
There you go. That would increase as well. So we are looking at something positive. Did you guys think there's, what did you guys think about the form of this?
It's gonna be linear.
I think it's safe to say it would be linear.
Yeah.
So, yeah. So that's good. And what about the strength?
Oh, I thought it'd be pretty strong. That like it wouldn't be like perfect, but there wouldn't be any like super, I don't know, like there wouldn't be a lot of deviation with a lot of the points, I guess.
No, that makes sense to me, what you're saying. I kind of agree. Well, I definitely agree. I don't think it'd be perfect. There's all kinds of atmospheric conditions that can cause the speed to change a little bit. So anyways, very good. I think that looks right. Group 3, you want to talk about yours? I'm going to go ahead and start you off with that. So group 3.
We put the distance in the X and the brightness in the Y.
Okay. All right, that says brightness. You have to trust me. Okay, so I can agree with that. Direction, what did you think?
We said negative.
Negative. All right. So let's put negative right there. What about the form of this?
We said strong.
Okay, so strong for strength. Did you think it's
Oh,
going
the
to be
form it said
linear?
also linear.
Oh, you also said linear.
Yeah.
All right. So this is pretty good. And you know, without having any other knowledge, I think it's safe. That's a safe thing to say. What's funny about light is that it actually falls off almost exponential decay. So in reality, this would actually be a nonlinear trend, and it'd actually be something like linear decay like that. But I mean, I'll tell you, this is not an AP question that's going to show up where they expect you to know stuff about how light falls away. But so everything you answered totally works for me. Okay, so in part D, we're comparing the weight of the car to the age of the owner. What do you think is going to go on there?
I think I was gonna say like no correlation and then weak.
Yeah, I think that one can be summed up pretty quickly. No relationship on this one. I mean, if there is, it's by accident. I think we could all agree there's not going to be a reason for a correlation between those two. And what I wanted to show you real quick is, and you don't need to go to this website on your own if you don't want to, but it's kind of worth a few minutes. It's actually called guessthecorrelation.com. And you can see it's like a game. It is a game. All right, so we want to guess the correlation right here. These are all going to be positive correlations, and they're all going to be in tenths, basically. Now, we could get more specific as we want. But what do you think the correlation of this one is?
Maybe like 0.7 or 0.8.
Okay, if you're saying 0.7 or 8, let's see if we can do that. 0.75. Look at that. It's actually 0.84, but we are close enough. They don't expect you to get it 100%. We're not going to do this too much. What about this one?
0.1.
0.1. Let's see that. Oh, wow. Look at that. That's higher than I expected it to be. It's a 0.18. I'm glad we went with 0.1. All right. And this one.
Point like 3.5 maybe.
0.35. Oh no. All right, and I think the point of this game, you don't have to be experts at identifying the correlation. That's not the purpose, but it is good to see, like this is a 0.58. And so it goes to show that even something that doesn't look super highly correlated actually can get a pretty high correlation. All right, so like we saw one more. Okay, that's not what I wanted. I'll just try a 0.5 on that one. Wait, did I? Oh. Okay, I put it in wrong. I said 0.5. Oh, that would have been perfect. Whatever the case, if you want to do this just to kind of understand what these correlations look like in practice, it's worth a couple minutes. Guessthecorrelation.com, but I'm not going to spend any more time with it right here. This next slide comes straight from your textbook. It is correlation properties. And this is almost worth, I forget the page in your textbook it's on, but you can find it. It's a standalone thing. And it's worth almost having this bookmarked in your book and just having it available in your notes when you're doing any problems, because these are just things you need to keep in mind. So the sign gives the direction, we know that. The correlations between -1 and 1. Some of these are not super complex, and correlation treats X and Y symmetrically, which means the correlation of X and Y is the same as the correlation of Y and X. So if we switched which one was our explanatory and our response variable, then the correlation would not change at all. That's actually a very important point. There could be some conceptual problems that come up related to that. Correlation has no units and is only ever presented as a decimal, never a percent. So if you have a 0.68, never say it's a 68% correlation. It's a 0.68 correlation. It is not, correlation is also not affected by shifting or rescaling the data. The last thing we talked about in Unit 6 was we could take our data and we could, if we have a distribution, I could shift it to the left, I could change the spread of the data and stuff like that. Now, imagine we do that with two variables, and I'm comparing using scatter plots. The correlation does not ever get changed as a result of this. So that is good to know. It only depends on the z-scores, and the z-scores stay constant. Correlation measures the strength of a linear association between two variables, and correlation is sensitive to outliers, so you'll see that change. And in fact, that's going to be something we come back to. I keep saying in chapter 9, but there we go. A significant outlier can have a major impact on the correlation. So this is essentially just ripped straight from the textbook. I could look up the page number. I don't have it available right now, but really important that you know these properties or have them available. Okay, correlation is not causation. So you've probably heard this before, that phrase. It is a correlation, or it is a catchphrase that a lot of people know, but it's important you understand. A correlation really doesn't mean anything about causation. And we'll talk about when we can say something about causation. Okay, so again, we're not going to answer this question just yet. I just want you to think about it. So the scatter plot is showing real data. This is a real data set that someone captured. They plotted it, and it's telling a story. But knowing that correlation is not causation, well, okay, maybe we will talk about it right here, because on the next slide, we're going to talk about the same data set even more. So what is this data trying to imply? Let's just say that. So just a reminder that explanatory variable is the national IQ on average.
That people with higher IQs make more money.
Okay, yeah, pretty straightforward. I think that's what the data here is showing us, and the data is real, so it's fair to make that conclusion. I think one thing that goes a step too far, and to get back to this idea, what goes too far is to say that having a higher IQ causes you to be a wealthier country, basically, because this is a per capita GDP. So, oh, well, if your people are smarter, that causes you to have a higher GDP per capita. and wealthier. So this doesn't, we can't say anything about causation. We can just say these two are correlated in some way. Okay, but now we can dive into this a little bit further with the idea of lurking variables. Sometimes two variables can be correlated, just like we see here. We have IQ and GDP per capita are correlated, but it's not because there's any kind of causal effect between them, but instead it's because there's a third variable which causes both of them to happen. And that's called a lurking variable. So kind of here's an example that I've seen thrown out a few times. Here's ice cream sales. So ice cream sales, and then here's drownings. So I know you can't really read my writing, but we're going to correlate ice cream sales and drowning. Okay, as ice cream sales go up, so do drownings. We could probably all agree that ice cream does not cause people to drown. So what do you think is making these two correlate with each other, that as one goes up, so does the other?
Maybe like rum flavored ice cream.
Maybe. So let's think of, first of all, temperature. There we go. So that came through in the chat. There we go. And I think that's good enough right there. When are you going to buy more ice cream? When it's hot outside. When are you going to go swimming? When it's hot outside. In general, maybe not you specifically, but in general, people buy more ice cream in the summer and they go swimming in the summer. And so that's really what's happening, that if we correlated ice cream sales to summer, there'd be a positive correlation. If we looked at drownings correlated with temperature, then there'd be a positive correlation. And so you get the idea. It's not, this is causing this to happen. Summer, or well, temperature is actually the better way of saying it. So the way it was put in the chat, summer is causing both of these things to happen, and this doesn't even exist. So if that makes sense, let's kind of look at this again. So what else might be a lurking variable? If we want to say that IQ causes wealth, that's a possibility. But what could cause both of these things to go up that's unrelated? Or not unrelated, sorry, that's not mentioned?
Could it be like length of education or something like that?
Yeah, that's a great answer. How much education are you able to get in these different countries? So in America, 13 years of education, K-12 is fairly standard. And, but going back 100 years, even 13 years wasn't standard in America. But you get the idea. So maybe we could just say education. And it doesn't necessarily, I'm not saying this is right, but we can agree that that's a possibility, that education, access to education, and things like that can affect both of those things. All right, I think the point is clear enough right here. So this is a basic idea that is mentioned in the chapter. I want you to be aware of it, but we're not really going to dwell on it. It's not going to be on your test at all right now. Okay, when we are given nonlinear relations in a scatter plot, we can transform them to linear relations. And that conceptually means identifying if we have some kind of a exponential, you can see right here, exponential, quadratic, cubic, logarithmic sort of relationship, and then doing the inverse of that to make it linear. So in this case, I believe this is a square root function. So if we squared it, we get that, a perfect linear correlation, or yeah, perfect linear relationship. So that's the idea of how we can make nonlinear things linear, doing the inverse. But again, for right now, I'm throwing the concept out there, but I'm not testing you on this. This will be something to get back to at the very end of the year. Okay, and then creating scatter plots. This is the last little bit, and this is what you need to do in your calculator. And I'm going to run through kind of the how-to, but then we're going to have an example that we're going to end class with that we'll use in order to actually run through the process. So you're going to need to create 2 lists in your calculator. Remember, the way you get to your list is you go to Stat and then Edit. And so you're going to have 2 variables. And you're just going to take those data points, put them in both your lists. Don't rearrange them. Put them in exactly the same order as they are listed. Okay, now we can create a scatter plot using our stat plot menu. Again, that's hitting second and y equals in the top left. So I'm not expecting you to do this right now. I'm just kind of throwing out the steps, and then we're going to run through it. Your explanatory variable will be the X list. The response variable will be the Y list. So the reason I'm putting this here is so if you want to come back to this presentation, you can kind of follow along with this. But we're going to see a data set in a second. Now we can look at the scatter plot by doing, by zoom 9. And we already have practice with that. You hit the zoom button, you just hit number 9, and then you'll zoom right into the scatter plot that you created. It's a pretty straightforward thing. And you know what, I actually want to skip this slide and then we're going to come back to it. So let's actually practice with that part of it right now. So we're going to be looking at a scatter plot for this. So go ahead, take these data points and put them into your calculator into list 1 and list 2, or whatever list you want. So now that we've got the scatter plot created, we actually find the correlation a different way. So in your stat menu, so you can go back to the main menu, hit stat, and you slide over to calc, and we've already gone there before for our 1 variable stats. But if you go down, you're going to notice a lot of options for things that end with reg, which means regression. There's so many different regressions. You have an exponential regression, a power regression, natural log regression, just so many different things. But the only thing we'll ever use in this class is number 8, which is linear regression a plus bx. We'll talk more about the equation of a linear regression tomorrow, but for now, just select 8. And once you have that, you don't need to worry about anything else. And you can just hit enter all the way down and calculate. And you'll certainly see 2 numbers there. You're going to see an A and a B. If that's all you see, then I'll explain how you can get the other numbers. But if you've already taken care of something on your calculator, you're going to see R squared and R given. And assuming that you guys already have this, and we'll talk about it in just a second, but assuming you guys have your R there, can someone just type in or write in what their R value shows? Don't worry about R squared right now. All right, there it is, 0.9653, and of course it extends, but very good. So did anyone follow those steps and all you saw was an A and a B and no R squared or R? Okay, so that did happen to some people. So here's all right, so go back to the main menu and or the main screen, hit mode. And you want to go down, and most of you already did this. I had you do this on like one of the first days. But scroll down until you find an option for stat diagnostics. And make sure your stat diagnostics is on. I have no idea why the calculator is set up this way, where they don't just automatically give you the correlation, but for some reason, it's an option you have to turn on. Do you have that option?
Yeah, I turned it on.
Okay. Yeah, so as long as that's on, it will remember that it's stayed on. and you don't need to keep turning it back on over and over. So it'll stay that way for the rest of the semester. All right, so if anyone still has questions on that, we can talk about that later. But besides that, that's it. You do your, and it all is right here. Your linear option number 8 in your stat calc menu. So you have linear regression a plus bx, and it will give you the correlation. Now you have to have the data put into your lists before you can do this, but that's all there is. And that takes a lot of work out of needing to do a bunch of calculations. Okay. So there we go. Now we have these numbers. We made a scatter plot. We could describe the direction, form, and strength of the plot. So if you look at your scatter plot again, and to get back to it, you don't have to do anything except hit zoom and 9. And you should pull up that scatter plot again. So how would you describe, and you can just verbally real quick, tell me how you would describe this scatter plot.
I'd say it's positive and then nonlinear.
Positive. We got nonlinear as an option. Does it look linear enough to some people? And this is one of those where I would say it's linear enough, though I can see why it has a little bit of a nonlinear trend. So I don't think you're off base by saying that. Here we might say it's linear enough. And sometimes we just don't have enough data. This is only 10 data points. If we had 100, maybe we'd see a very clear nonlinear trend. Of course, maybe at that point it would look very, no doubt about it, linear. So that's one of the dangers of having a few data points. Okay, so if we called it positive, and let's say we called it linear, would you call it strong, medium, or weak?
Probably strong.
Strong. Okay, there we go. All right, it says write a few sentences telling about what the plot says about the data. And I mean, just in general here, just to wrap this up, we could say that as the weight of the static weight of the truck increases, or as the weight and motion of a truck increases, so does the static weight. And it looks to be following pretty closely. So anyways, find the correlation. We already have the correlation. You guys know how to do that. If the trucks were weighted, or sorry, if the trucks were weighed in kilograms, how would this change the correlation?
Would it change the correlation?
What do you guys think? Would it?
Doesn't it not change the correlation?
That's right. It would not change. This is, when it talks about this, this is referring to rescaling the data. So we could, multiply all this or divide this data by a certain amount, the 2.2 right there, in order to get the kilograms. But that is just rescaling data. The z-scores don't change. And so therefore the correlation is not affected. So very good. And do any points deviate from the overall pattern? What does the plot say about a possible recalibration of the weight and motion scale? Does it seem like we could just do a recalibration and get these points to align, or the data points to align a little better? I might just answer this one real quick. There's a really nerdy way we could approach this. And this is kind of jumping ahead to tomorrow, what we want, and I'll let you go very soon, I promise, what we want is these two to be perfectly correlated. It's never going to work out that way in reality. What we want these to be is perfectly correlated. And we want it to be that if this is 10, that this is 10. Now, not only do we want it to be perfectly correlated, but we want it to have a specific equation for this line, y equals mx plus b. We're doing essentially that same function. I'm going to talk about this tomorrow. It's going to look a little different for us. It's going to look like this. But it's still a linear function. Again, I'm jumping ahead into tomorrow's and chapter 8 stuff. But what we want is this intercept. I'll just use the old one that you guys are familiar with. We want this intercept to be 0. And we want this slope right here to be 1. So we could recalibrate this and try and get that ideal formula so that we get a perfect y equals x equation formed out of this. They are equal to each other. That's getting pretty nerdy and into the weeds. But bottom line, I think you could just come up with a way of saying, yes, we could just recalibrate this a little bit and we could figure out, how to get this weight and motion system to work. Okay, that is it for today. Let me show you your homework. It's available online. Okay, there's a few things here that are holdovers. I'll probably talk about those tomorrow because we're running up to about the time that everyone wanted to leave a long time ago. So anyways, if you have any questions on anything, stick around. Otherwise, have a wonderful day and I will see you tomorrow.
Thank you.
Thank you.